Thank you, Daniel, and welcome everyone. We're going to talk today about comparing SQL to TypeQL. This is actually a talk that I gave at our conference at the time Graken Cosmos last year in January, where we presented effectively how TypeQL differs to or compares, and actually in some ways is similar to SQL. And today we're going to do that again. If you have questions, please drop them in the chat box. Do remember to hit to all panelists and attendees. The default is set to all panelists, and then only Daniel and I can see the comments.
Paul Bergman with this is an excellent example of how that looks like in the chat.
Exactly. Yes. So let's start with a little bit of history, because I think looking at the history of relational databases, SQL, and more specifically relational theory is actually quite fascinating. And if we go back all the way to 1969, 1970, there's a few seminal papers that were published, but in particular this one from Edgar Codd, where he introduced a relational model for large shared data banks, where for the first time ever he introduced the notion of a new type of mathematical formalisms to represent data in a different way, because at the time we used navigational databases, network databases, hierarchical databases to manage our data, which had a lot of complexity. And when we actually wanted to fetch data from there, we had to know the physical way of how this data was actually stored. So Edgar Codd, or Ted as they would call him, he would ask his team out there in San Jose in the valley, that sure, you can express the question by writing a navigational plan, but the navigational plan is not the essence of what you're trying to accomplish. So wouldn't it be nice if you could express the questions at a higher level and let the system figure out how to do the navigation? Basically, what Edgar Codd is trying to propose is how can we create an abstraction layer of the physical layer and actually write queries that make sense or don't require us to know the physical way of how the data was stored. And now, the problem with some of Ted's ideas is that relational algebra, relational theory, while very simple in the core ideas, the way it was explained was mirrored in mathematical notation. And so it took this paper from Donald Chamberlain and Raymond Boyce to actually introduce SQL as the language to actually query relational databases or databases that implemented the relational model. And SQL became very, very popular because SQL was written in English words, and it was accessible to people that didn't require to effectively have a background in math. And that basically formed the basis to which later on and until now, relational and SQL dominate and rule the world when it comes to databases. So for today's talk, there are some parallels into actually what Edgar Codd is trying to do with relational theory, and in some ways, what we're trying to do with TypeDB, especially from a conceptual point of view. So there's three things that we want to get from today. Now, the way we would describe SQL is as a language that you can read and understand intuitively, enables you to ask questions at a higher level while letting the system figure out how to do the lower level operations. And hopefully by the end of this talk, I hope to be able to show that actually the way we describe, or when we refer to here as a language, is that we could say the same thing about TypeQL. And we're going to come back to this later. And so the three key things is that a language that is intuitive, that you can understand intuitively, enables us to ask higher level questions and lets the system figure out how to do lower level operations. Now, in order to answer that, we're going to cover three things. So first, we're going to look at how to model data, both in SQL and relational and TypeDB, how to read and write data in a relational way, and finally, how the hypergraph and the automated reasoning in TypeDB allow us to represent or to effectively do things that we simply cannot do in SQL. So first, let's take a step back. And if we look at and what I think a lot of people that have learned SQL will be familiar with, this is a simple entity relationship model. Now, when we go about modeling our data, we would normally start with some sort of ER diagram, go through a normalization process, find our, for example, our functional dependencies in order to get to the tables that we can actually implement in SQL. So effectively what the normalization process means is that we go from conceptual level, which is the ER diagram, to a logical level, usually a third normal form. And that's where we stop. Because, and that's the beauty of the relational model, is that the DBMS gives us the physical independence of data, because we don't have to actually point to where it's actually physically stored under the database. Now, how does this differ to TypeDB? So if we go back to this entity relationship model, if we look at this section right here, TypeDB's model is a direct implementation of the entity relationship model. So the way we model it from a conceptual perspective is directly of how we model it also in code. So if we look back at this database architecture, what this literally means is that we skip out that normalization process, and rather than just giving us an abstraction over the physical level, what we see here is an abstraction over the logical level. So we can model things directly and only at the conceptual model using TypeDB's schema. Now let's take an example. So this is a famous, if anyone has learned SQL, especially in a Microsoft environment, they'll be familiar with the Northwind dataset, which is a fictitious trading and which is a fictitious shipping trading company where we've got suppliers, products, employees, orders, shippers, and we're going to use this as a way for us to understand and to look at some examples of how we can model things and ask questions to the data. So we take one table here and we start to define some schemas. Now, if we take a product table and we simplify it a little bit, in the product table, we'll have a primary key, we may have a foreign key, a bunch of columns. Now, how would this compare to in TypeDB? Now, firstly, this depends on our modeling decisions, but this is a fairly simple example. So we'll probably say that the products table should be modeled as an entity of type product. We then say that the product will have some attributes, a product key, product ID, and a quantity per unit. And then we still have that foreign key, the category ID. Now, if you're coming from an SQL background, you may be tempted to actually create another attribute and have that as a foreign key. But that's wrong. That's what we don't want to do. Because what we want to do, and most of the time when we see foreign keys, that's actually where we want to create a relation. Because what a foreign key is simply doing here, at least, is connecting a product with a category. So we want to have an assignment relation that assigns a product to a category. And this is where we have to use the right names to denote the type of relation. In this case, we chose to call it an assignment relation. And then we also have the roles, the role that a product plays and the role that a category plays. So here we can say that the product plays the role of product assignment in an assignment relation. Now, how does this look in code? Now, in SQL, to create the table would look like this. Versus in TypeDB, we would use the keyword define to effectively define a schema. We then say, use the keyword sub to declare that a product is an entity. The product has some attributes, in this case, a key. So the product ID is a key. It then has some other keys as well, some other attributes that we define here as well. And then finally, we also declare the type of those particular attributes. So product ID is an attribute of value double, for example. Then we've got the foreign key. Now remember, the foreign key is not modeled as an attribute, at least in this case as in TypeDB, but actually is assigned as a relation. So what we want to do in the schema, we want to say that we allow a product to play a particular role. Specifically, the product can play the role of assigned in an assignment relation. And that's how we would declare or define that relation. We say assignment sub-relation relates to two other roles, a category and assigned. So having looked at some basic modeling structures, how do we go about reading and writing data? Now, the way we're going to answer this question is from a relational point of view. So we're going to be looking at some of the more common relational operators. And at the end, we're going to see actually that the way we would think of those relational operators doesn't necessarily apply directly to TypeDB. But let's first start with how to insert data. So let's say we're inserting a new product with product name chocolate, product ID 12, quantity per unit 421, and category name confections. On SQL, we'll probably insert it like this, where we're connecting the category to the right product. Whereas in TypeDB, we would want to create a relation between the two. So we want to fetch something that already exists in the database, which we use with the keyword match. We then say $C is a category, which effectively matches us for the confections category, and we assign that to the variable name $C. We then want to insert data. So first, we want to insert the product. The product has some attributes. And finally, we create a relation between the categories, which already exists in the database, and the chocolate. And we do that by creating a tuple that you see below there. $C and $P are in an assignment relation. So here you see again, rather than assigning a foreign key, in this case to chocolate, we're instead connecting it to a relation. Do you like chocolate, Daniel?
I do indeed. Yeah.
I think most of us in the office do like quite a bit of chocolate. Yeah. There is quite a bit of chocolate as well.
Quite a bit.
And then at the end of the week, there's no more chocolate left. So let's move on from chocolate. So how do we read data? Now, the most common way of effectively, the structure would be a select from where statement in SQL. The equivalent in TypeDB would be a match get query, where match fetches us allows us to say that, hey, we're looking to match for some data. And the get keyword allows us to specify what variables we want to be returned. So let's look at projection. So let's say we want to return all product IDs and their unit prices. So we're effectively just wanting to create a projection from this table just for those two columns. So a product ID and a unit price. Now, to think of this query in TypeDB is quite different to just thinking as taking a table and creating effectively a projection of that table. Because instead, what we think we want to do is take an entity, in this case, a product, and we're fetching for the attributes of those entities. So that's conceptually how we would think of the query. Now, if we look at restrict, in an example of a restrict query, it could be return the product IDs and product names for products with a unit price higher than 12.5. So we add a restriction here in the column unit price, which in TypeDB would simply mean that we're still fetching for product ID and product name. Those are the variables that we put in the get statement. But we say also that the product must have an attribute, unit price, higher than 12.5. And then we can add that filter in the query. Then if we look at union, so let's say we want to ask, get all the different cities in which suppliers and customers are located. So we've got two tables that we want to union. The equivalent query in TypeDB would be saying that give me a city that's connected to a customer through a located relation, or a city that's connected through a located relation to a supplier. And then for all of those ones that satisfy those conditions, fetch the name of the city, and which is modeled as an attribute attached to the city. Now, intersection simply means that give me a list of cities where both customers and suppliers are located, which in a sense looks the same as the previous one, but rather than saying or, we say and. So we want the city to have a relation to a customer and to have a relation to a supplier. And the most famous operator of them all, a join. And by the way, we're just going to look at a natural join because in terms of demonstrating the difference, left join, right join, it effectively boils down to the same thing. Here we want to return the corresponding category names for each product name. So we're creating a new table that puts together the columns category name and product name together. Now, most of the time, what this basically means in TypeDB is simply to say that the product is connected to a category through an assignment relation. And the category has an attribute of type category name, and the product has an attribute of product name. And then fetch me those values of those attributes, but only if those entities are connected to each other through the assignment relation. Now, to take a step back, we've looked at how to do relational operators in TypeDB. But what should be clear, hopefully, is that if we consider SQL as a direct comparison to TypeDB, it's important to actually keep in mind that the model that TypeDB offers is very different to a relational database. And one way of thinking about it is that the modeling decisions that we made in a relational database are effectively imposing a tabular structure on our data. And that means that we've modeled the data in a tabular way. But what if we didn't have to enforce some sort of tabular structure? And that's kind of where TypeDB comes into play, because some of the modeling decisions that you may have made then could have been very different to a relational database. And that's why like-for-like comparison is actually very difficult between the two. And in the third section, we're going to look at what the hypergraph and the automated reasoning actually give us that a relational database doesn't do naturally. Because like I said, the modeling decisions that we would have made in TypeDB would be quite different to the ones that were made in a relational database. And so if we take the Northwind dataset again, we could ask ourselves, how would we have modeled this differently? And we could look at these tables right here. So the suppliers table, the products table, the employees table, the orders table, and the customers table. And the way we could have modeled this is actually quite interesting, because rather than having 5 separate tables, we could actually put suppliers and customers in one table, and then represent them through a sale relation and a stocking relation, where a company plays either the role of customer or the role of supplier, depending whether they are selling or depending whether they are stocking. There's also an interesting example of a ternary relation right here, which is an instance of a hyper relation, where we've got a sale happening between a company, an employee, and an order. And that sale relation is represented here through this hyper relation. And then lastly, we've got a containing relation where we can model also attributes on that containing relation, where the order contains a product, where the product is stocked through a supplier. And how do we model this in the schema? So first, we would probably start thinking, what are our entities? In this case, we've got 4: an employee, a company, an order, and a product. We then may want to also define the relations that we have. So we've got a sale, we've got a containing relations, we've got a stocking, and here you see the different roles that we've created. So under sale, we've got a seller, a placed order, and a customer. And then we simply declare which entity is allowed to play those roles. So an employee can play the role of seller in a sale relation, and a company can play the role of supplier or customer in either a stocking or a sale relation. And queries that we consider to be traversal queries are also quite interesting. And those are simply queries that touch a lot of different things in the database. In this case, for example, let's say we're asking, return me all employee IDs who sold to a customer based in London of customer demographic X. Now, here what we're effectively saying is that we've got an entity employee, that's connected through a sale relation to a company, which in turn is connected to a customer description. We don't define the type of relation between the company and the customer description, but we do want to be returned all the employee IDs that satisfy those filter in that pattern. And we can very easily represent that in effectively in code, which would look like so first in SQL. And in TypeDB would look as follows, where the relations allow us to define the connections between all the different types of connections that exist. So as we see, the employee, for example, is declared as a variable with the $S sign, and then we put that as playing the role of seller in a customer relation, in a sale relation where the company plays the role of customer. And then TypeDB also offers the ability to do type-based reasoning. So we can create type hierarchies in TypeDB. And what a type hierarchy basically means is that, let's say we've got an organization, and our organization has got two subtypes, a for-profit one and a non-for-profit one. And we can subdivide those ones even further. For-profits can be banks, can be pharmaceuticals. So here we're saying that all organizations, all pharmaceuticals are all organizations, but not all organizations are pharmaceuticals. And to represent this model, we can, again, quite easily do this in the schema in TypeDB by using the keyword sub. So any type, anything in TypeDB can actually be subtyped under one another. And besides type-based inferencing, TypeDB also offers rule-based reasoning. So let's say we've got a transitive relation or a transitive rule, where we're saying that if X is connected, if X is located in Y, and if Y is located in Z, we want to say that X is also connected in Z. And that rule can be represented like so. First, as part of this is part of the schema, we say that if X is connected to Y, and if Y is connected to Z, that's all declared in the when part of the rule. Then we say that X is connected to Z. And where could we apply such a rule? Now, if we look at on the bottom left here, we've got employees connected to territories, connected to regions. So with that rule, and this is where it gets really cool. Let's say we have a question, return me all employee IDs who are in a region with region description X. That query we can actually simplify by simply saying employees connected to regions. Now, even though in the model, if you remember, in the model, regions are not directly connected to employees because they go through territories. But if we have a rule, we can basically abstract away the need to ask also employees connected to territories, connected to regions, whereas in SQL, we wouldn't be able to actually represent that as a rule natively in the database. And we can take more complex examples here. Let's say we ask, return me all organization IDs of any type of organization that employees have sold to who are in a region with region description X. Now that effectively would, let's assume there's two types of organizations. So there's charities, there's companies, and they will have orders. Those orders will have sellers. And those sellers are in territories which are in regions. And we want to make sure they're only in one type of region described as X. Now, this is where the reasoner in TypeDB becomes particularly interesting, because the queries become fairly verbose, especially because we have to write out all the different permutations that can exist, plus also the traversal paths that the query must take. Whereas in TypeDB, we can very simply, with the right rules, we can simply say, fetch me an organization that will infer all the subtypes, all the charities and all the companies without having to declare them one by one. Then fetch me an employee. the organization is connected to an employee through a CL relation. There's also a region with region description X. And finally, we say that the employee is located in the $R, which is effectively the region with region description X. And finally, we get for $CI. So here we start to see that effectively it's not necessarily about counting the lines of code, but it's a useful proxy. But of course, in the TypeDB query, there's a lot of logic that has been abstracted away. But when you are querying for this data, you don't have to worry about that underlying logic, because we can take this even further, where we can abstract away. This is a 150-line query in SQL, and write that in only 3 lines of code in TypeDB. So finally, if there's one thing hopefully to remember from today, is that at an architectural point of view, what TypeDB, especially on the modeling side, implements is a direct implementation of the entity relationship model. And in that sense, what TypeDB provides is an abstraction over the logical model. So you don't have to normalize our data, and we can simply model things at the TypeDB code base at a conceptual level. And that's why we describe TypeDB as a language that you can read and understand intuitively, enables you to ask questions at a higher level by letting the system figure out how to do the lower level operations. So thank you very much.